Check, 1, 2, 3. Test, 1, 2, 3. Yep, that looks good. All right. So the first thing I'm going to do is pass out some syllabi. And syllabi is plural for syllabus, if you didn't know that. And also a checklist for lab reports. So there's more here than you actually, there are students. I made some extras, so parents, if you want an extra copy, you can have one. So please take and pass. So how many of you have another Libertas class or Libertas, however you want to pronounce that, depends on if you're being more like, original Latin or more like American sounding about it. Libertas. How many of you have already had classes this morning? Okay, 1, 2, yeah, is anyone not? Okay, so in that case, I'm gonna not go into too much detail about stuff you've probably heard about already, like Praxis School, you guys are accountable for this class for what's in the Libertas handbook, and that goes for all of our classes. So just a few things to point out with that. First of all, homework needs to be on time, and if it's late, it becomes a 0, unless it's excused in advance. So that's standard across Libertas. So, and what I found last year was as people were getting used to it, at first there were a bunch of 0s, but then everybody got really punctual, so it worked, I think. So yeah, make sure your stuff is on time, and if something's going to be late, or if you're going to be absent, just let me know in advance. So one other thing, I'm guessing probably nobody has a waiver or the acknowledgement page of your handbook signed that you need to turn in still? Everyone's probably already done that? Okay, good. All right, and everything that you need for the class is, as far as online or anything, is just Praxis School. So hopefully you all have a student account set up and your parents have accounts set up. Your other teachers have probably talked to you about that already, so I won't go into it. But if you have any questions, you can ask me or one of your other teachers. I did send out a Google Drive folder for you guys. That's totally optional. If you didn't get that email and you want it, you can just let me know. But personally, I just like to have all of my resources stored in one place so that I can just look at them at any time rather than having to find links in homework or whatever. If you want to use that, you can, but you certainly don't have to. And if you didn't get it and want it, again, just shoot me an email. I'll send you the link. I really like Google Drive and storing things there. So anyway, the homework that's listed on Praxis School, I believe I am doing it the same way that every other teacher is doing it. But if you find that the way I've listed my homework is different and is confusing to you, then let me know. Just say so-and-so, name the teacher, is doing it differently, and then I'll make sure that we do it the same way. But you'll notice that on your student portal in Praxis School, I've actually put all of the homework for the entire year out there. So you can already see all of it. Don't panic, don't let your head explode. When you see all of it there, just it's all dated. So it tells you when you can start working on the homework. And note that I wrote the due dates, like I said, due by whatever at the top of every assignment. So they're actually listed, the way it's recorded, Praxis School says the due date is the date that you start working on it. I did that on purpose. That's so that you can actually see the homework earlier, because otherwise it'll only post the assignments on their due date, which is kind of weird, unless I go into some weird settings. So I believe I'm doing this the same way that all your other teachers are. Let me know if anything appears different on Praxis School, but the actual due dates are going to be the ones written in the description, where it will say at the top of the homework assignment, due, and then a date. Does that make sense? Okay, great. All right, and I've also posted lesson plans with them, so you can ignore those if you want, but if you'd like to know what we were doing in class, especially if you're going to be absent or anything like that, the lesson plans are all there too. All right, moving on. Today, by the way, is going to be the most boring day of the year, I hope. So, as first days often are. Anyway, I'm going to, yeah, I guess that's not really necessary. I already went over that. Yeah, that's pretty good. Anything I grade of yours, I'll try to get back in a week or at maximum 2 if it's like a test or something. There will be a bunch of tests and exams, and on your syllabus, which I just passed out, it'll tell you the grade breakdown. There's a few types of grades in this class. Most of it is homework. So what that means is if you turn all of your assignments in on time, and I don't do a thorough check, you grade it yourself, I just make sure that it's complete, and I give you a complete grade, so that's 100 on that homework. if you turn it in on time. If you don't turn it in on time, it's a 0, and if you don't have it graded when you turn it in, then it's an incomplete. So as long as you were consistent with turning in your homework on time, that's what, 50% of the grade it says on the syllabus? 40. Yeah, so that's a lot. That's a lot of your grade just handed to you right there. So get in a good rhythm with that. And this class actually does follow a rhythm most of the time, where what we're going to do is, generally speaking, I'll introduce a module, which module is what we call chapters in this book. So it'll be like, for any given chapter, module, generally what'll happen, first one I grabbed is pink, oh well, is we're going to do like a lab experiment. And Annalise, is this visible on the computer?
Not really.
Not really. Okay, is it a color thing or is it a distance thing?
Distance.
Okay.
I mean, you can like see the words, but if you get up close, you can kind of see them.
I'll write bigger.
But
I'll try to. All right. So typically, like, we start each module with an experiment to introduce it. And this will be on the same day that we take a test on the previous module. So like when we finish module 1, you'll take the module 1 test in class, and then when the test is over, we'll do an experiment for module 2. Then the next week, I go ahead and introduce the module. So I'll teach you all the stuff that's in the chapter module first, and then you'll go home and read it yourself for homework. And as you're reading it, you're going to do the on your own questions, and in the homework is listed OYO questions, O-Y-O, but that stands for on your own questions. So during the module, as you read, it'll have little questions interspersed throughout. So you answer those questions. It's easiest if you do it while you're reading, I think. And then you're going to grade those questions using answers to them that are found at the end of the module. So, you know, first week there's an experiment, and I give you a whole week to do your lab report, which is really, you know, I don't recommend waiting a whole week, but I give you that extra time anyway, just in case there's something weird in your schedule and you need to take longer to get around to it. Then at the weeks when I introduce a new module, you read it, you answer the on your own questions, and if there are any examples in the chapter, in the module, then do those examples too, but I don't collect them, you just do them, all right? And then every time we do a module, we introduce it, but then the next week we review it. And when we review it, you reread it at home, and then you do the study guide that's found at the end of the module. So in the actual textbook are your on your own questions for the introduction week, and the study guide questions for the review week. And the answers to the study guide are actually found in your your answer key and solutions, tests and solutions book. So you can find the answers to the study guide in here. So one thing though, and this is in the Libertas handbook, so this will be true for every class, we don't want you to have the answers in front of you as you're doing the homework. Make sense? Use this to check your work, and again, if it's not actually checked, like if I get the work and it's not graded, how do I grade it? Like how do I count it? Incomplete, right. So if you want full credit, make sure it's checked. And if you're not in the habit of, like, you know, writing a check mark next to every correct answer, it's an easy way to tell me that you have graded your work if you do that. But if for some reason you really, really don't want to do that, then just, like, I don't know, have your parent write, you know, graded and initial it or something like that. So it's easy for me to tell. All right, any questions so far? That's just kind of basic format of the class. Any questions? All right, good. And of course, I'm always just an email away if you ever need anything during the week. So, all right, let's talk a little bit about physical science. Oh, and one other thing, during lunch. So, at least in the handbook, it says to take your stuff with you during lunch and not to eat lunch in the classroom. So since this is the period right before lunch, I don't know if that still applies because we're going outside nowadays, but it's what's in the handbook. So anyway, I guess you can ask Miss Tina or something if you're not sure. Or maybe I will for the whole class, but obviously not right now because we're in class. So anyway, all right. So what do you think science is, just in general? That might sound like kind of a dumb question, but how would you describe science as a whole? And you don't have to raise hands, generally speaking. what separates, for example, science from, I don't know, like theology or faith or something like that?
So like basically how the world works.
Okay, how the world works, that's good. All right.
What we can explain.
What we can explain, I like that. Now, let's dive into that a little bit more. How are you explaining science?
Facts.
Okay, facts. I'm just going to write that as its own thing. Facts and how the world works. That's kind of similar, I think. What we can explain.
Be like experimenting.
Okay, so you're getting onto the right track with this as far as like how we explain it. What we can explain. All right, I like that. Experiments. All right. Now let's talk about the difference between just like facts in general and then facts that we can explain. Like in science, how do we explain the facts that we're addressing?
Experimenting.
Experimenting, yes. So experiments are going to be part of the method. All right, what else is involved in the method of science? Now, this will be kind of, this is so obvious that you're probably not thinking of it. Oh, Bo, yes.
What, isn't it a hypothesis or something?
Okay, yeah. So we're going to talk about steps in the scientific method. So we will need a hypothesis. I'll put that here. We're going to come back to that in a moment. Okay. So if you're going to do an experiment and actually like, you know, get results out of it, what do you need to be doing with those results? And the answer, just don't overthink this at all. Like think the most basic level.
Thinking.
Okay, so thinking, good. So there should be reason. There should be like, you know, actually thinking logically about what you're doing. And so thinking will definitely happen a lot on the front end when you're designing your experiment. But then in order to get any information out of your experience, what do you have to, or your experiment, what do you have to do?
Research.
Okay, so research will be another part, good. And you guys are still thinking too much about this.
Do something.
Even more basic. Science is about
Map the materials.
even more basic. That's it, Rory, yes. So observation, very good. So yeah, all those answers are correct. The one I was fishing for was observation. So yeah, science is a method. It's going to involve specifically things that we can test. And the way we test them is going to be that we actually have to observe them. So science is going to be built on observation. Now, let's get some actual, like, more formal definitions on the board. So these are just like a couple of low-hanging fruit dictionary.com definitions, which dictionary.com, by the way, is actually like reputable. You can source it in something serious, you know, it's not Wikipedia. Wikipedia is usually accurate, but anybody can edit it, so you don't really know for sure if they're credentialed or not, and if they know what they're talking about. I don't know if I'm going to enjoy this board. All right, well, that'll work now. So some definitions of science. I'll use a different color, so it'll stand out from the smear, hopefully. Oh, black. All right, science. Okay. I like this beginning, systematic. So you're using a process, you're using a system. I do encourage you all to take notes in class. It's just a good practice in general. Systematic knowledge. Of the physical or material world. Gained through observation and experimentation. So observation, just think through the senses. And the point of experimenting has a lot to do with the fact that you only want to test one thing at a time. So you can make scientific conclusions just by observing the world around you, but if you really want to test something, then make an experiment where you're only testing that one particular thing. There's no other variables involved. So I'll give you an example. If I say that, gravity is going to make this marker fall, have I just proved it? Yeah, I mean, I've just proved it pretty well. But if I want to really, really prove it, then what I need to do is I need to put this in an environment and test it again where like there's not really going to be any factors going on except for gravity. So, for example, like when an astronaut went to the moon and he drops objects on the moon and they still fall, but at a different rate, that's a little closer to, a good scientific experiment to have a test like, just now when gravity is present, but there's also other factors. And then on the moon where, some of those factors are eliminated. Now, can we actually get a situation where like there's no factors at all except for gravity? Maybe. Anyway, in experiments, you isolate your variables, meaning like you just focus on one thing and you run different types of tests on it so that you can, control for the variable, and I'll talk later about what that means. All right, so another definition of science, I'm going to put it over here just because I ran out of room. I'm used to writing enormous. So, used to be like one of my secret superpowers to write really, really, really small. All right, so systematic study, again, is something to emphasize from that, so I'm going to just go ahead, or systematic knowledge, but systematic in general. Over here, I'm going to actually define physical science. What do you think this is the difference between physical science and science in general?
Physical science has to do with like materials and things, versus other science can kind of be just a lot of theories and hypotheses and stuff like that.
So it definitely deals with physical things, and science in general will tend to deal with physical things, like there or there. But it is true that like in physical science you're going to have a lot of exact like hands-on application rather than just being like theoretical. So that's good. What else? Any other thoughts? And so the name's kind of misleading because it says that science in general is going to be about physical or material things. So why is a physical science not just like a science? Isn't that kind of redundant? So it is going to be like sciences in general are going to deal with the physical world, which you can test, and that's one of the reasons why like for example, it may be true that God exists, but you're not going to scientifically test that probably, because under normal circumstances, I suppose, it's a little harder to do, through observation, etc. I mean, people can make arguments to the contrary, and that's fine. But I think most like scientists would at least make the claim I just made, and I'm not even saying I defend it or whatever. I think for example, Jesus stepping into the world, that's God interacting with the physical. But can you scientifically prove that, for example, God exists if you don't observe him? The observation is a key part of science. So anyway, so we're not going to be dealing with like theology. We're not going to be dealing with other things when we're in the realm of science. But I will ask this question, and this is a big, important question, but it's one that we can't fully address today. Maybe we'll come back to it throughout the year. Is there a difference between scientific reality and all of reality? Like, for example, is it like, oh, there's the truth about, there's like faith-based truth, and then there's scientific truth, and the two don't really mix? What do you guys think?
Some things you can't like scientifically prove, and that's why you have to have faith.
Mm-hmm.
Some things like God, you have to have faith and believe in him.
That's good.
You can't scientifically prove that he's real, so you just have to believe.
So there's a difference definitely in like how it's proved or whatnot, or you can believe based on faith in the absence of observation, that kind of thing. So that's a good point. So any other thoughts? So just in general, one thing that like kind of in another one of the classes I teach is philosophy, so I'm not going to get too far into this, but in general, there was a point in philosophical history where people started to say there's a physical reality and then there's a spiritual reality, and they're totally different. And what may be true for the physical may not be true for the spiritual. And I'm not even talking about like laws, like does gravity apply to God? I'm not saying things like that, but like, just like, do truths about science and truths about God like still exist in the same reality? I would argue yes, and we'll talk more about that later. If that was just like, huh, what was that about? Don't worry about it. We'll get there later. But I think it's a fair statement, and you can disagree with me on this if you want. But just like in a biblical worldview, I think it makes sense to say that all truth is anchored in God. You know, He's the creator. He's the one who made the physical world, and so there's not going to be any contradiction between physical scientific truth and the truth of who He is. So all truth is anchored in Him. All right, physical science. Sorry about that rabbit trail. This is going to be specifically any of the natural sciences dealing with inanimate matter. I'll break this definition down once we have it up on the board. What does inanimate mean, though, first of all? Yeah, not living, good. Not living, not moving. But I mean, it could be moving, but not moving on its own will, if that makes sense. Or of its own volition, I guess. Sciences dealing with inanimate matter. Or, another thing is energy. And then they list some types of physical sciences as physics, chemistry, and astronomy. So those are some examples of physical sciences. Physics, chemistry, and astronomy. It's not all of them, necessarily, but let's name some sciences that aren't physical sciences. So remember, what makes it a physical science is, like all sciences, it's dealing with the physical world, but specifically it's dealing with inanimate matter. So what would be a type of a science that is not dealing with inanimate matter?
Maybe like botany or something?
Very good. That's excellent, yes. So botany would be an example. Because plants, they're living, right? They're, you know, they're not like as animate as, you know, we are. They can't like, you know, choose to walk around at the speed that we can or anything like that. But they do move, and they grow. They're living things. Yes. Zoology, perfect. You guys are getting the hard ones first. What else? Yeah.
Oh, anatomy.
Very good. Anatomy. And I'll add physiology because that's kind of goes with it. Anatomy is like how the body's built. Physiology is like how it works. I'm no expert on that, but I think that's a fair statement. What else? Think even bigger, like what contains all of these? Starts with a B. B-I-O.
Biology.
Yeah, biology. So yeah, all these things could be kind of like sub-branches of biology. And I would say another thing just to throw in there, maybe genetics. So if you're dealing with living stuff, you're not dealing with physical science. Physical science will be, you know, like physics, chemistry, astronomy. You're dealing with dead stuff. So we're doing a whole year of dead stuff. Isn't that funny? But yeah, physical science is huge. It incorporates just about everything, you know, except for biological type things. And there may be other things I'm missing. I'm sure there are. But and of course, this is not dealing with, like, for example, whole new category like social sciences, or you know, you don't have like political science in here, or economics. And those are really more like what you would call a soft science. Like, they're not as mathematically driven. They're not as much like, you know, if this happens, this will always result. You know, in like political science, you could have this particular thing happen, and then people respond to it in all different ways. You know, it's not like you can make a mathematical formula about it. But the great thing about physical sciences is you can boil it all down to math generally. You know, and you can make really precise calculations in physical sciences. And now, one last question before we move on. In these fields here, do you think that the physical sciences have to do with any of these? Like, can you apply the physical sciences to your study of botany, zoology, anatomy, genetics, and biology as a whole? I saw a head nod. Yeah.
Yes, probably. I would say yes.
Any ideas of how?
I don't know.
Let's say, for example, you are really hungry and you eat an entire pot of very, very spicy chili. And then there's a chemical reaction in your stomach starts burning. And so then your doctor, who studied anatomy and physiology, he knows what's wrong with you. He knows he needs to give you a bunch of antacid. So how is he applying one of the physical sciences to the study of your body? Yes?
The chili to the anatomy of the person.
Mm-hmm. Yeah, and so what kind of a reaction is going on with the chili in your stomach? And yeah, it's a chemical reaction. It's chemistry. So chemistry is coming into play. Yes?
Didn't you say also, so we're studying like dead things, so like zoology would go into that because they're actually living before they're dead.
So this is a good point. All of the matter that everything is made up of, you know, and especially if you know, something dies, you know, the body left over, all the matter that things are made up of are subject to the laws of physical science. So yeah, and that applies to, you know, like you were saying, zoology, but also just like, you know, the reactions going on inside of anyone's bodies. It's all dictated by chemistry. And then even when the things die, you know, then the matter left over, you know, it's just, it's subject to physical science laws. So very good. And you know, you could study like a zebra in the field of zoology, but if you want to study the chemical composition of the zebra's hair, then what you're doing is you're applying chemistry to it. They say the most basic science is physics, and that's one of the physical sciences too, but we'll talk about that in the spring, actually. So, questions, thoughts, comments before we move on to our first experiment? Okay, great. So we're going to do a lot of experiments in this class, and you're going to do a lot of lab reports. And not every single module has a lab report, but most of them do. And you know, I'll warn you that the lab reports can seem kind of intimidating at first. But you get used to them, and really it's like, you know, once, I would imagine, I haven't asked them, but I would imagine if you asked last year's students, you know, like, hey, how hard were lab reports by the end of the year? They'd probably say they got really used to it, and it's just kind of like then they could do them without thinking too hard about them. The main thing about lab reports for this year, this is, you know, still a pretty early science, but I'm guessing this is the first time any of you have done a lab report, right? No? Okay, some of you have before, good. All right, so what we're basically doing is the lab report is about doing the scientific method properly. It's about taking, you know, often very simple experiments, and you might just kind of be tempted to say like, okay, I did this and the results were this, and just leave it there. But practicing the lab report, it does a couple things. Number one, it helps you to really understand the scientific method, and number two, it'll help you to really like analyze things in the scientific way, and so that you can eventually create your own experiments. And then I guess number three, it teaches you to communicate your experiments with other people. So really the purpose of a lab report, whenever anyone does a scientific experiment, it's not enough for someone just to say, you know, eureka, I cured cancer. Everybody has to, it needs to be more like, eureka, I cured cancer, and here's my experiment that I used to do it. And then several other scientists, lots of other scientists will read that lab report of the experiment, and they'll say, okay, well, we need to make sure, so we're going to test it, and we're going to do exactly every detail of what you said in your experiment and see if you came up with the same results. And then if your findings don't pass that test, then guess what? You didn't cure cancer. People won't accept your findings. So lab reports are really important. And the idea of a lab report is basically you tell people exactly what you did in your experiment, exactly what you saw, so that they can do the experiment themselves and then see if they get the same results. So everyone has a copy of that and the syllabus. Where'd the extras end up? Probably down there by you, James, or Vale? Oh, over here, perfect. All right, so we're going to talk about the parts of a lab report. First, though, I'm going to pass out some supplies for the experiment. And I have, I didn't know how many tables are going to be set up, but I have a total of 3 of these experiments that can be done. So maybe this table, that table, and then the back table, and you two can just go wherever you want. All right. You can pass that to them. Did I give you scissors? I didn't need to give you scissors if I did. Maybe I didn't. So this first experiment is going to be pretty easy to set up, and then there's a lot of waiting involved. But we can use the waiting time to discuss how to do these lab reports. All right, so if you can open up your science book, in Module 1, just go a few pages in, and you'll notice there's a green section. And the green sections in the book are the experiments. By the way, I should throw this out here. If you are like me and you prefer listening to books rather than reading them, you definitely want to read this book because there's a lot of visuals that are important. But there is an audio version of the science book, and you can get it on Audible. You could even create a free trial and get it. But then when I ended my free trial, having gotten the science book with it, then I could no longer open it, really. So what I actually did was I played it at like double speed or something and recorded it and made my own files out of it, so that then when I couldn't access it through Audible when my account ended, I still could in my files. But anyway, you can buy it, and then that saves you a lot of time. All right, so this is experiment 1.1. In your lab report, there's some things that I'm going to be, and just so you know, this is actually like a standard lab report that the different science teachers are using. So I actually got this from Carla Wilson, but then I just kind of like changed the wording for some of it. But mostly it's even just her wording. So if you use this format, you get good at it this year, it's going to make your life easier next year, and then the year after that, as far as I know anyway, if everyone's still keeping to that. So I want your lab reports to be typed. You'll take detailed notes in class, but then you'll type them at home. And so they need to be typed single-spaced, 1-inch margins, which is just normal, 12-point font. Now you need to put the title of your experiment at the top of your lab report. And so it's got to have the experiment number too. So experiment 1.1. Atoms and molecules. You can go ahead and write this down because this will be, you'll be taking notes on this experiment in class and I'm typing it up later. So now we're going to label different parts of the experiment, which are all the different sections below. So we have, first of all, purpose. Then we have a section called background. And this shouldn't be, this should be vertical on yours. I'm just doing it horizontal so it'll fit on the board. But you can just space it out like on this checklist, how it just goes one to the other from top to bottom. Materials. I may run out of room. Experimental procedure. And each one of these is an important part in the scientific process, by the way. So results. Oops. Discussion. And yes, I ran out of room. Conclusion. And the last one is error analysis. Technically the second to last one, I guess, because you're also going to have your references. And for the references, every week it'll be the same. I don't think we're ever going to have any other references. Maybe once we will. But just copy what's written down at the bottom. Copy Wiley JL Exploring Creation with Physical Science. And I did give you guys an electronic version of this. And actually, every week that you have it in your homework to do a lab report, there's a link to the electronic version of this checklist. So you can save it on your computer in case you lose it. But also, you can copy and paste your reference. So why do you write a reference? Why do you source things in general? Basically, if you use somebody's work, you got to give them credit. And so that's what the references will do there. So now let's set up the experiment, and then we'll talk about each part of it. But I guess we need the purpose first. So the purpose, we're going to write like a research question. Where did I put my, oh, here it is. Black on black, it's hard to find. All right, research question. All right, for your purpose. So I'm going to write RQ for research question. Can electricity break molecules down into the atoms of which they are made? Sorry, this is too small. Erase references so there's more room. And can it cause new molecules to form? First of all, we need to do the background section before we really answer that. The background section will include our hypothesis, which is what we think will happen. So we need to define atoms and molecules. You can get the definitions from the book. But what you do in the background is you give any background information needed to explain what you're doing in the experiment. So you need to know the definition of atoms. You need to know the definition of molecules. And for time's sake, because we are running a little bit low, I'm just going to tell you right now, and you can go and find the exact definitions in your book later, okay? So atoms are the smallest chemical unit of matter. And so you have a picture in the front flap of your book, the periodic table of elements. And that's a list of all the different types of atoms. And they're the smallest chemical units of matter. Next week, or next class, we'll talk about what that means. Molecules are going to be two or more atoms linked together that make a substance with unique properties. So for example, what's the most famous molecule ever? Probably H2O. That's where you have two hydrogen atoms and an oxygen atom linked together. And oxygen by itself has certain properties. You know, you breathe it, it's combustible. Hydrogen has its own properties, it's highly explosive. But then you put them together into water, and this molecule has unique properties that are, you're not going to breathe water, it's not going to explode in the same ways. In our research question, we're basically asking about things that we defined in the background. And so do you think that if we, and I'll give you the basic experiment design, what we're going to do is fill each of your jars about 3/4 of the way full of water. I'll come around and do that. We're going to mix in some baking soda. So add 1 teaspoon of baking soda, which I'm going to pass out. Where did the baking soda go? Shoot.
You don't have it.
Oh, you have it all. Great. So go ahead and put 1 teaspoon of baking soda in and then pass that around. And stir it up. So what we're going to do then is we're going to, after that, you're going to take your wires, and your wires are made out of a particular kind of an atom called copper. When you have a lot of the same atom, it's called an element, so the element of copper. So you got a few atoms in play. You have oxygen, hydrogen, you have copper, and then one of the elements in the baking soda is carbon. So do you think that we're going to see any of the molecules, like for example the water, break apart when we run electricity through it? That would be part of your hypothesis. And the hypothesis is what? Yeah, it's like an educated guess about what you think is going to happen in the experiment. So the last sentence of your background, in your background you define things that I tell you to define. You don't really have to define anything else necessarily. And then you have a hypothesis. So do you think you're going to see first of all, electricity breaking molecules down into the atoms they're made of? And if so, what do you think you'll actually observe in the experiment? You can tell me. Is your guess?
I think we'll see the baking soda separate from the water.
Okay. What else? Everyone's got the baking soda stirred into your water, by the way? All right. Do you think you're going to see, like, if the water molecule did break up into hydrogen and oxygen, what would you see?
An explosion?
Maybe?
Nothing.
What's that?
Nothing.
Maybe nothing? Maybe you can't tell? First of all, water's a liquid. What is oxygen? What is hydrogen?
A gas.
So if you saw a gas, water becoming a gas, what do you think you would observe if that happened? We don't know. Now, what's that? Yeah, less water is one thing. Now here's another thing. Do you think that any new molecules are going to be formed out of these various atoms? This one, I doubt you're going to be able to guess the result. But I'll give you a hint. There's a reason we're adding carbon to the mix. All right, so now it's time to set up the experiment. So what you're going to do is you're going to take your two wires and you're going to attach them to the two terminals on your battery. So like wind them around, make sure they don't touch each other, but wind them around each terminal. And then someone on your group can set a timer. Now I will sometimes allow you to use phones in class, but only when I just like outright say you can. Right now is a time when you can, because you can set a timer, and we're going to count 10 minutes of running this experiment. In fact, let's all do this together, maybe. Maybe I'll just do one timer, and I might have to shorten it because we've only got about 12 minutes left of class. So is everyone's battery set up?
No.
Okay.
When do we start the timer?
What's that? I'll tell you when.
He's gonna start.
I guess I'll do it. Yeah, I think I'll just do it. All right. And if you think you have yours ready, then let me know and I'll demonstrate it to the class. Like I'll show everyone. That looks pretty darn good. Yeah, so do that with the other one.
I'm having trouble connecting these.
That looks pretty good.
That one. Oh, sorry, I messed up.
And if you want to tape yours on, you can. I brought some tape. But before you do that, dang it.
Yeah.
Now you can also see which end of your wire is longer, because the longer end is probably easier to wind. So once you have it ready, then take the non-battery ends of your wire and dip them into your water when we start the timer. So, anybody want tape? This tape has a little baking soda on it, so don't freak out about that. I'll just cut you a section and go around. There you go. Okay, so go ahead and tape it on. And we're going to do a little bit less than 10 minutes, but I think it'll still be fine.
I think we might have it done.
Good. Yeah, it looks great. All right, so when you stick it in, you should notice something happening immediately.
Wait, you shouldn't or should?
You should. I really should have been taking this video like on one of the experiments.
Oh wow, it's bubble.
I guess I can.
Wait, I don't think. Where does it go? Which way?
Yeah,
All right, so everybody ready?
Once you've got it on, you can.
You can start your timer now. Your timer could just be running a little faster than ours. Now it says about 10 minutes. Okay, starting now. All right, I'm gonna move this around. Yeah, I really should have set this up earlier. All right, are you seeing anything happening yet?
Yes, bubbles.
Great, bubbles. All right.
Would you like to see them? I can move the camera over here.
Yeah, thank
so
you. I'll turn this around so that you can just keep the camera on your experiment. And anybody watching at home, sorry I didn't do this right at the beginning. What we have is we have these wires attached from one end to the 9-volt battery, then running into the water, which has been mixed with baking soda, 1 teaspoon of baking soda. It's all stirred up, and we're letting it sit for approximately 10 minutes, but we're going to go a little bit short of that. All right, so while this is going, first of all, note what you see immediately. It's important in an experiment to write, roughly when things happen. Does something start instantly, or does
Can I
something
still see
happen
it?
over time? As part of just being precise with it. So, what does everyone see?
Well, the copper looks like it's like corroding almost.
Okay, what color do you see developing on the copper?
Silver.
Okay, so it's turning like a silverish color. Someone says green. Okay. So as this is happening, since you're already seeing some results, which is very good because we're running out of time. Real quickly, before we get to the results, the next step in your lab report, you do the purpose, which is a research question. You do the background, which is definitions of anything that you need to explain for people to understand the concepts behind the experiment, and end it with your hypothesis. So first of all, is anyone's hypothesis already coming true? In part at least? Like if you hypothesize bubbles, maybe, or something like that. And your hypothesis, by the way, it can consist of, if you want, like, and I say generally do this, kind of a broad statement of, like, in general, like, do you think that, like for this one, that atoms can break molecules down and then build new ones? I mean, that electricity can be used to do those things. But then also, like, what are you going to see in this particular experiment based on your belief in that? All right, so materials. This is the part of the experiment where we list every single material used. So what are the materials that we've used in this experiment?
Batteries.
Jar, water, copper wire. What type of battery? We used a measuring spoon and or a spoon. That sounds insignificant, but we've got to be thorough. And if you didn't use all of the supplies, like the book may list some supplies that we don't use. So what we're actually doing is we're listing what we did in class, even if that's a little bit different from the book. That's a very important thing, so I'll say that again. What we're doing is we're recording in this experiment what we did in class, even if it's a little different from what's in the book. If you just copy everything in the book, you're not going to have a true lab report if we didn't do it that way in class. And sometimes you won't, but most of the time you do it more or less. And we also used baking soda, that's important. And finally, we used electrical tape. Is there anything I'm forgetting?
A glass jar? Oh wait, no,
Okay, yeah, I got that. Jar, water, copper wire, 9-volt battery, measuring spoon.
Water. Yeah, water.
Water, baking soda, electrical tape. I think that's everything. All right. So keep glancing at that as we're talking about this. The experimental procedure, you explain everything that you did. And for that, you can actually use the experimental procedure in the book and just change it slightly if you need to. But basically this will be fill the jar about 3/4, wound the wire around the battery terminals, etc. So I'm not going to go through all the process, but you're going to write down exactly what we did in class in this procedure. All right? Now the results. Really, we should wait the whole 10 minutes, but we won't have time. Because class ends in like 4, and we got 5 minutes left.
I have a question.
Yeah, please. Yeah, so this is actually, I'm going to get that in a moment, but so this is the part where people get messed up in their lab report. There's a difference between the results and then the discussion and the conclusion. Results is literally just what you see. It's like if you weren't thinking and you didn't understand what was going on, just listing what you see. So here, I was tempted to explain what that stuff is, but I'm not going to. I'm just going to, because we're in the results phase right now. So while we're in the results, just write that you saw it, that you saw weird blue stuff. Some floating, some on the wire. So results, we saw tons.
Bubbles.
And were the bubbles instant? Alright, so I'm going to write that down because that could be helpful. And we're seeing weird bluish stuff.
Oh no,
Greenish. I'll say blue, green, you write however you want to describe that. Some of it is on your wires, right?
Yes.
Some of it is just floating around though, right? If it's not yours, don't say it is, but if it is yours, then say it is. Alright, is that everything we're seeing?
Whoa, look at it, just floating.
The wire change color.
Wire change color?
Yeah, green things?
And someone see anything else? Okay, so those are our results. We are not saying why these things happen. We're not saying what we think they are. We're just saying what it looks like. Does that make sense? All right. Then, after that, in the discussion section and in the conclusion section, that's when we're going to start interpreting what happened. So the discussion, we're going to write, it says write a paragraph that analyzes and discusses your results. At minimum, explain whether or not your hypothesis was supported by the results. So what we can do here is we can actually say why we think the results are happening. So why did we see bubbles? Could it be that we see bubbles because electricity is splitting up the water molecules into two different gases, oxygen and hydrogen?
Perhaps. Yes, but it also needed the help with the baking soda.
So, yeah, what about the baking soda? This is something you're really going to need to read the book to know, but I've already read the book like a bajillion times because this is probably like my 15th time teaching this class. So this is my 10th year of doing homeschool teaching of some form or another, and every single year I've taught this class, and sometimes I've taught it more than once. So, yeah, we're seeing the bubbling because we're splitting this up, but then we're seeing the green stuff, the blue-green stuff, because electricity is causing the carbon and the copper and one or two of these other ones, I can't remember, to react and form together into something called copper hydroxycarbonate. And you can read in the book to flesh out this portion of your experiment, because the book will explain what's going on, and you can use that to help you write your discussion. So the last part of, sorry, it's probably hard to read all of this. The last part of your discussion portion is that you were going to explain whether or not you saw your hypothesis fulfilled. So, did anybody see things that they predicted in their hypothesis? Okay, great. Then say yes and write what those are. All right.
What you wanted to.
So class is over, but I'm going to just real quickly. Something to note from your experiment.
I have 30
We
seconds.
only timed it for about 9 minutes, for 8.5 minutes.
Mine was set for 9 minutes.
Okay, great. Yeah, so the rest of you can write down that we only timed it for about 8.5 minutes. And finally, with your experiment, I'm just going to cover this real fast, so I'm not going to keep you for much of your lunch at all. In the conclusion section, you're going to explain, you're going to kind of link this back to your purpose. So you can say, like, in this experiment, we showed, we did answer our research questions, and we showed that electricity can break down molecules, and it can help form new ones. And in your conclusion, you should also note if there were any, the experimental errors actually part of the conclusion. Right, so you list if there were any errors in the experiment, like anything that happened in the experiment that would give us wrong results or just not give us good results. And then write any ways that you think that you could make the experiment better. So if you don't think there were any errors, write it. And if you don't think you can improve the experiment, write that. And that's everything. We finished this time. All right, thanks very much. Anybody had a question?
Oh, I was going to ask what the EA was, but...
Yeah, that's the error analysis. Just what's wrong, is there anything messed up in the experiment?
Yeah,
Like, just to give you an idea, if somebody dropped blue, green ink in the experiment, then that would taint the results.
Yeah.
Something like that. That would be a dramatic mistake. All right, thanks everyone. Sorry.
Do you want this recording to stop or something?
Yeah.
Why don't you? Oh wow, y'all can like photos.
Yeah.
But before I do, I'm just going to point out that you can see on one of these, you got this blue-green substance. I don't know if you can really see that very well. It might be too close up.
Yeah,
But this one that I'm wiggling, it's got some blue-green copper hydroxycarbonate, caked onto it. And this one is pretty clear, and then the water itself is blue-green because of the copper hydroxycarbonate.
Can I help you clean this stuff up?
Yes, please.